Hello, committee. My name is Harish Gokul Krishna Kumar, and I'm here to present my master's project, DeepObserve, building AI-assisted observability for consensus protocols. I would also like to present three supporting projects: DocStore, PipeQL, and zRPC. Let's start off with DeepObserve, an AI-assisted eBPF protocol visualizer and profiler. The problem statement. Observability is defined as how well you can infer the internal state of a system from its outputs. So these outputs could be logs, metrics, and traces, and they help gauge system health, performance, SLOs, etc. But there are a few key challenges in observability. Manual instrumentation uses language-specific SDKs. The telemetry logic and application logic need to be co-located, and there's a need for individual tools to accomplish specific goals. For example, visualizations require log ingestion using Loki or Elasticsearch. These are high volume, high cardinality outputs. Continuous profiling requires Grafana Pyroscope or language-specific profilers like PySpy for Python. So what's the approach? eBPF allows you to run custom sandbox programs inside the Linux kernel without changing its source code. So we can leverage eBPF to create low-code, language-agnostic observability tooling, and observability can be implemented as a sidecar. And that's precisely what DeepObserve does. We use one sidecar instance, which pulls from a database cluster, and the sidecar exposes a web UI and REST endpoints for agentic and MCP use. So ResView is the visualization tool, and ResLens is the execution level visualization tool. All right, let's start with ResView, visualizing consensus algorithms. So here are the features of ResView. ResView helps trace and visualize requests through any consensus algorithm. We focus primarily on PBFT, which stands for Practical Byzantine Fault Tolerant Protocol. This is sort of the fundamental BFT protocol. It helps visualize each protocol stage, for example, pre-prepare, prepare, commit stages, etc., and also helps visualize subprotocols such as commitment, view change, checkpointing, etc. It displays real-time message flow and timing information between replicas and clients, helps measure latency across consensus stages and quorum formation, and helps observe leader changes and faulty replica behavior. It also provides an MCP-enabled interface, which allows AI agents to autonomously trigger workloads and visualize PBFT execution flows. Also, we migrated ResView to a new architecture. The previous one included manually instrumented visualization modules of over 600 lines of code to extensible modules using lightweight eBPF hooks, which take up less than 250 lines of code. So the design of ResView is as follows. Due to C++ symbol mangling, we need to add a lightweight layer of hooks and instrumentation. So there's just a few lines of formatting code. The sidecar spawns a BPF listener, which is a BPF trace program found in most Linux distros. We define BPF programs for each module, and these modules target various subprotocols like commitment, view change, checkpointing, etc. These modules listen for events from lightweight hooks we have defined in our codebase as eBPF uprobes. So for example, the ResDB trace PBFT commit state is the code which is present inside our codebase. And the uprobes are defined as a separate module, and these essentially print out or they emit logs. So the hooks are called from the actual consensus logic, the code on the bottom right corner, where if the state is changed, then we do some business logic, and then we just call these lightweight hooks. The eBPF uprobes emit these logs as printf statements. These are then parsed by the sidecar and exposed to consumers through UI, MCP, AI agents, etc. So there are a few nice features about ResView, so let's go over them. When all replicas are non-faulty, we can see a visualization. So this is basically with primary as replica 3, and all replicas are healthy and non-faulty. This is the real-time message flow information. So it's essentially a granular, a different type of UI for the graph. where each stage is essentially timestamped, and there is the timing information for each stage. This is a scenario for one faulty replica, where in consensus, in PBFT, in a system of 4 replicas, one can be faulty. So there's a leeway of one replica being faulty, 3F plus 1. And when one is faulty, or when one goes down, how does PBFT, the consensus algorithm, look like? So that's a visualization. There's also the view change subprotocol. So what happens when one replica goes down, becomes faulty? There is a view change or a leader election, which happens. So R3 was the old primary. Now R4 becomes the new one. Now let's go over a demo of ResView working in action. And let's start off with a prompt. Simple as that. And now we kick the AI agent into action and see what results it can come up with. So it uses one reference, and it basically sees that, hey, can we use this commit key value from the DeepObserve MCP server? So I'm going to type in allow. It ran the commit key value function, and then basically checks the request ID as demo key 1. So it essentially opens this up, and it basically sees that, hey, for this request, it essentially goes to replica 3, and then it goes into the prepare phase, where there is a quadratic communication process happening. Then there's a commit phase, where there's another quadratic communication phase happening. And then there's basically this reply, which is happening. So 2F plus 1 messages in the prepare stage, 2F plus 1 messages in the commit stage, and then F plus 1 in the reply. So let's basically ask the AI if it can come up with it, right? And I'm also going to attach a screenshot of this. So I can quickly select this element and embed that in. And now we kick the agent off into action. So it comes up with, what is PBFT? What are the main phases? So the client request, the pre-prepare, the prepare, commit, and the reply. So why are there so many messages? Because PBFT is designed to tolerate up to F faulty nodes and out of 3F plus 1. So that's the total number of replicas which are needed. So what you're seeing, the visualizer, is the colored arrows represent a message between the nodes, and it basically, you get the point, right? So let's ask it, can you explain some subprotocols of PBFT, such as view change? So this kicks the agent off into action. And again, it basically picks up and says that, hey, what does view change essentially entail over here? And these are the few things which it comes up with. So basically detecting a faulty primary, initiating a view change, selecting a new primary, the new view messages, and then resuming consensus. So let's simulate it. Let's take theory and put that into action. So I'm going to attach this as my context. Use this tool to stop the current primary. So this is just a helper function to simulate faulty behavior. So the AI agent basically uses the bash tool in order to visualize this. And this means that now the primary is basically done. So this basically goes into the database, and it tries to sort of like commit this message, but now the primary is down. So a view change is supposed to happen. So let's see how that works. All right. So we went ahead and sort of saw that the demo key 2 got committed into the database successfully. So we take the sequence ID to track it. So I'm going to say that, hey, use this as a sequence ID to track it using trace request. So you can either use the key which was committed, or the sequence number which was generated from the consensus in order to do so. So it looks like, since replica 3 was faulty, the new replica became, the new primary rather became replica 4, and the consensus diagram changes. So now it goes to replica 4. 3 is not active, so it does not send out the view change messages. Since we have 2F plus 1 replicas, which is 3 replicas, we can still sort of like do consensus and move ahead in terms of liveness, and ensure that the value gets committed into the database. So if we scroll down, we can also see the view change happening. So this is the leader replacement view. As you can see, the old primary was R3, the new primary is R4, and there was a quorum which was reached. So essentially, quadratic communication again for leader election, and then it essentially broadcasts, sends everybody that, hey, this is the new view, I'm the new primary, here you go. So thank you. This was DeepObserve, protocol level analysis, code level analysis using low overhead eBPF and agentic inference. Hope you liked it. All right, let's take a look at ResLens, visualizing call stack and code execution. So the features of ResLens are that it profiles the runtime execution of consensus protocols using language-independent eBPF instrumentation. So this is a zero-code instrumentation tool, but there's one requirement, which is that the debug build of the database or the process which is being profiled is a requirement. It correlates low-level function execution with PBFT protocol behavior. The custom flamegraph library is essentially used for this purpose. We developed this in-house, and this also helps us add some really cool features like linking spans to the actual source code. It also provides AI-assisted summaries and explanations of flamegraphs, and also a MCP-enabled interface, which allows AI agents, sort of these MCP tools, to explain runtime behavior interactively. All right, so let's take a look at the design of ResLens. So we use an open source tool called Pyroscope for profiling. So we use version 0.37.1. We use an older version of this tool, and this is to leverage its ad hoc eBPF profiler. It was removed in the newer versions. We use the eBPF spy tool to attach it to an already running process. Pyroscope provides a server which exposes flamegraphs on port 4040. It also provides a client, which is what we configure to listen to our process. We just use pgrep-f kv service, which is the name of the process, to essentially list out all process IDs, and we just connect to it using Pyroscope Connect. To analyze flamegraphs, using AI, we convert the flamegraph to Markdown using this tool called pprof. So it essentially converts this flamegraph information rendered on the UI to a Markdown, which we then feed it to an LLM. All right, so let's look at some features of ResLens. So flamegraphs can be viewed in a split view with a table for execution time and flamegraph on the right-hand side for a detailed breakdown. So the table view essentially provides self and total, self being the time taken by that function, and total is the time taken by that function plus its child functions. So to view those child functions or callees, we also have a view which we call the sandwich mode, where callers and callees can be viewed. So it helps investigate which child functions are called by a parent function. We also have flamegraph spans linked to source code. So this is the custom UI integration which we did. So this makes it easy to navigate to the code base from a function span on the UI. So what happens if you want to call, let's say, consensus manager dispatch? We just click on that span, we view code, and takes you to the GitHub page where the code is located. Pretty cool if you ask me. And there's also the AI assistant, where this is a simple flamegraph analysis. On the left-hand side, when AI is unavailable, and on the right-hand side is the AI breakdown of the profile. So essentially, it uses the information from the pprof tool and breaks it down. So we see here that state polling and spin logs take up about 25% of captured samples. So we need optimization here. And there's some cool suggestions which the AI provides as well. Then we also have the MCP integration, where this can be invoked from your IDE. So you can just query, say, generate a flamegraph of the PBFT flow and explain which function is used to set or commit values. And the UI and the necessary tools are spawned by the MCP tool. So let's take a look at that in action. So let's start off with a prompt. Let's try out, how can I generate a flame graph of the PBFT flow and explain which function is used to set or commit values into the code base? So let's type this in. So we are using Copilot, and we're using GPT 4.1 as our underlying model. So as we see, it uses one reference, and it calls DeepObserve's phrase profile tool. Specifically, it calls the query, which is set value, and interval as now minus 30 minutes. So in the last 30 minutes, what are the occurrences of the set value function? All right, so I am essentially going to increase this. We see that there are no set value functions which are found right now in the flame graph. So let's simulate it. We are going to go in here into the integrated simple browser or the UI and click on one of the utility tools, which is fire set values. This is going to start inserting in some values into the BFT database and really try to get some tracing data for what essentially is happening. So here the set count is set to 1000, but we can stop at 500 requests. All we need is 30 seconds of tracing data, and then we can essentially provide the flame graph. So let's try to refresh it, and there we go. We have a few functions which pop up currently. So I'm going to do stop seeding because we already see the functions here. And I'm going to essentially click on a couple of things. So I don't know which function to click here. So let me see what the agent came up with. So my question was, can you use or generate a flame graph and also generate functions or give me functions in the code base which are used to do this operation? So it basically went over the code base and it basically said that the functions used to set or commit values are consensus manager, consensus commit, and consensus commit. And as you can see, we are using the PBFT module from the consensus manager. This is being done on top of an open source blockchain database called Apache ResilientDB. So the actual database calls this KV executor set method. And if we try to sort of like see, we see that there are a lot of set which are being called. So if I wanted to sort of like not narrow it down and see from like a high level standpoint, I can have set. And so I'm going to see what exactly is being called here. So turns out that ResDB, then there's this namespace called storage, and then there's this namespace called rest level DB and set value. So let's go to that function and see what's going on. So I'm going to click on the sandwich mode to actually see which functions are being called. Let me go in here and name that as set value. I'm going to essentially see all the functions which are called as part of this workflow, right? So as you can see, the total sort of like time for profiling is about 0.03 seconds, which is quite fast if you ask me. Then we call the transaction executor, the execute function, the batch data with sequence, a bunch of other functions. And then we actually call the set value with sequence. And then there are a bunch of level DB functionalities which are being called. This is really nice because through one query, now we can check which function is part of the call stack from the code and also view that dynamically as part of the runtime information. This is extremely good to use, especially for students, developers, early researchers who are essentially tasked to go into this code base and figure out for themselves. So it's a very nice telemetry tool to have. Thank you. This was DeepObserve, protocol level analysis, code level analysis using low overhead eBPF and agentic inference. Hope you liked it. Thank you. All right. I would also like to share some supported projects or some extra work which I've done. The first one is DocStore, which adds native support for secondary indexes and ResilientDB. So the motivation for this project is that ResilientDB had two modes of storage, an in-memory storage of snapshotted blockchain state as a hash map, as an unordered map in C++, and a persistent data store storage, which is level DB, a key value store. So these key value stores do not support querying by a secondary attribute. And to circumvent this, we synced our database state to an external database like MongoDB. So this required application developers and users of ResilientDB to set up a MongoDB database, constantly sync the state and sync all the data present in ResilientDB. So there was a requirement to have a logical partition of data for application developers to tune, configure, and view their data natively. So this was the motivation for DocStore, and this is version v0. So the design for DocStore is that secondary indexes are created using embedded indexes. So these essentially use Bloom filters to filter out reading unnecessary tables, files on the disk. So these are called as SS tables, and each SS table will essentially have a min and a max value stored to essentially apply range queries and to help find them better. We maintain a different mem table for each secondary attribute, a Bloom filter, and serialize this information to the SS tables, to these files themselves. Then when a query is fired, and if data is present in the mem table, then it returns it. If not, then we use the Bloom filter to filter out all the unnecessary SS tables, files in the database, to reduce read latency and read from a filtered list of SS tables. So this work was done on top of some work which was done at UC Riverside. And the paper and the paper implementation can be found in these links. We implement our V0 version atop LevelDB. So each key is a string and a value is serialized as a JSON value. Users can create a collection or a logical partition. Each collection creates a separate LevelDB instances. Indexes can be created only during the start of a collection. So it's embedded, it's sort of set in stone once it's created. Each collection maintains in a hash map with its key as a collection name and a unique pointer to these different collections. And the hash map is sort of wrapped with a mutex for concurrent access. The doc-store implementation can be found in the link below. And here is a diagram. So a client request comes in, and there are 4 replicas, each having a KB interface and a document store interface, which wraps over these various collections. All right, so let's look at the benchmark and some results. So here I have some numbers, but I want to give a live demo of how this works. So let's go to our project. I have the doc-store project opened up. Let me hit document bench test. And this is going to essentially run our benchmark test. So the first one is going to be BM insert. BM get is essentially going to be a get query, which is run. Then we do batch inserts. So this is just to see what is the latency of our set operations. Then we do some concurrent operations. And then the numbers which we want to look for here are the ones in the bottom half of this benchmark. So these are essentially going to be get by secondary key, get by secondary key using get all, range by secondary key, range get using get all, and get all. So as you can see, the get all essentially queries everything in the database and then applies a filter versus get by secondary key, which uses our secondary key attribute to filter these records. So this was sort of the bench test running in action. So the speed up, which is essentially perceived for the point query, is about 37x, and the speed up for the range query is about 8x. So this was a really cool project, and we got a lot of performance benefits by applying these optimizations to the storage instead of offloading it to the client, by allowing them to have a different database, by allowing the client to sort of like do these sync operations. All right. So we'll move on to my second supported project. This is going to be PipeQL, a pipeline query language with MLIR-based execution engine. All right. So the motivation for PipeQL was that traditional SQL was invented in the 1970s. It became part of the ISO standard, but it later turned out to be very non-intuitive because it does not have sort of a declarative pattern, right? So the logical flow of data is not linear. If we have nested of queries, then the first inner query gets applied, and then those results are used in the top query. So it's sort of like inside out. The point is that it takes like prerequisite knowledge to write good SQL, and understanding SQL is not that easy. SQL is popularly used in relational databases, and when we go towards NoSQL databases like MongoDB or Apache Cassandra, then these languages sort of fizzle out, and each database implements its own query language. So that's where the motivation kicks in. The architecture for PipeQL is that you have a standardized language, which is PipeQL, and then you would have an MLIR engine. So MLIR here would be a tool which converts a PipeQL, a query language, a language into an intermediate representation, very much like how languages like C and Rust get compiled down using the LLVM compilers. And then these MLIR dialects can then be targeted to different databases like MongoDB, LevelDB, ScyllaDB, etc. So that's the core idea. So what we essentially want to do here is we want to define a language, a front end for the language, and then use MLIR to compile it down into an intermediate representation, lowering it down to assembly code or code which can be executed against, let's say, Apache Arrow or LevelDB or any sort of storage engine. So here's the implementation idea. Defining a DSL, which is syntax, tokens, etc. Parsing the PipeQL query, for example, from users select star into an AST, defining attributes, regions, and semantics of our MLIR dialect. We define a visitor class to traverse the PipeQL AST and convert it into MLIR. And then this just allows us to lower the IR which is generated from this step into a stage where the base representation can be executed against the runtime shim, which is going to be the storage engine, right? So here are some implementation details. We essentially implement the from, select, and the where clauses. And this is essentially running on a Ubuntu 22.404 distro with 4 CPU cores and 8 GB RAM. So let's take a look into that in action. So here in my editor, I have a PipeQL syntax, which is essentially from users, a table, select star, select all the columns where age equals 25. So the way this is going to work is first, we're going to use a tool which we built called PipeQL to MLIR, which is going to take in this SQL statement or this PipeQL statement rather, and compile it down to MLIR. So we execute that. It takes up about 3.9 milliseconds to traverse, make this into an AST, and convert it into MLIR. So that's what the MLIR is going to look like. So this IR is going to consist of a module, functions, and essentially a relational algebra query. And here you can see that all the different type of optimizations like constant folding and other compiler-based optimizations is done when the IR gets lowered down into different stages. So this is what the IR or the intermediate representation looks like. We want to know what the final result looks like, and that is going to be displayed as follows. So we essentially take that, we use the run MLIR tool to convert this MLIR, and we run this against a test directory or a database. And there you go. That's the result. So in our table, the SQL statement from users select all columns where age equals 25 brings out this tuple, this row, which consists of ID, name is John Smith, the age is 25, 6.675 milliseconds. So this is the total execution time for the query to go from a PipeQL query, all the way down producing the results. I'd like to present my last and final supporting project. This is going to be zRPC, a RPC library for RDMA-powered consensus algorithms. So the problem statement for this project is that fault-tolerant consensus protocols require multiple communication phases, and these communication phases are usually quadratic in nature. The limitation of traditional networking is that the TCP/IP stack introduces multiple copies and overhead, and this increases latency in the consensus commit hot path. So to improve communication efficiency in consensus systems, we explore RDMA-based networking to reduce overhead and latency. So the background in consensus is that it involves very network and communication intense protocols, often in the magnitude of quadratic or of n squared in nature, since each node talks to every other node. And this visualization is actually pulled from ResView. So what can we do to alleviate this, to optimize and make this more efficient? So we essentially leverage RDMA. It stands for Remote Direct Memory Access. And this allows a zero copy application layer to network interface card communication, right? So essentially has a OS bypass feature where data flows from your application directly to your NIC using DMA and some hardware specific NICs. So let's take a look at how we can achieve TCP semantics using RDMA. So our use case is pretty simple. What we want is we want to design a NS2 server to accept N clients and a fast API client to do point and broadcast operations. So they're going to be N listeners, or rather N clients, and there's going to be one listener on every server, and each server is also going to act as a client. So the approach here is to build a RPC library called zRPC. RPC stands for Remote Procedure Call, and the model network calls as simple methods or functions which can be invoked. And we use a PI-EMPL, a pointer implementation design pattern, so that we can swap out our implementation of the actual RPC to different protocols or different strategies. So here's one strategy which I would like to walk over in detail. So let's say, for example, you have multiple clients which wants to talk to a server. Now the server has a shared ring, and each client is essentially going to get a unique offset in this shared ring buffer. And all these clients essentially go talk to the mailbox, and these are going to be atomic operations, which are carried out using the RDMA FAA feature, which stands for atomic operations. Now, once a offset is achieved using this atomic operation of getting the address to where to write to, the client writes the request at the free region. Then the server gets the offset from the RDMA notification using what we called a write with immediate. And then once the operation is done, once a message is processed, the server updates the mailbox so that the next client can get a peek at what the free slot is. And that's what this paragraph aims to say. So we implemented this in a Cloud Lab cluster, and we tested this locally as well. And here are some results for it. We take a look into two specific values. That is going to be latency and throughput. So here's what the latency numbers look like. The average latency versus the number of requests basically state here that the latency for TCP sort of goes up and down because of the kernel overhead and sort of these copies which is created, and it's sort of non-linear and not predictable. The RDMA-based communication, on the other hand, the RDMA being a shared ring and the basic ring being another implementation of this, is essentially constant, meaning that it does not get affected by the overhead of system calls being made or any other noisy neighbor process running. And the same can be applied through the throughput as well, where the throughput for the RDMA solution is extremely high. It's 9.4 to the 10 to the power of 3K requests per second. And that's larger than the TCP, demonstrating improved communication efficiency under consensus workloads. So those are my three projects. I would like to sincerely thank Professor Adoghi for giving me the opportunity to work at this lab, to work on all these cool projects. I'm also very grateful to Professor Pollack for introducing me to the areas of compilers, MLIR, and providing me the opportunity to work at a lab as well. I would like to thank Professor Rebak for supporting and encouraging our RDMA work, which eventually became zRPC. I'm grateful to my peers, collaborators, members of both Expo Labs and DevSec Labs, with students who I worked. And yeah, that was my presentation. Hope you liked it. Thank you.